Hi, my name is Alex, and I'll be walking you through my analysis of Lab 3, and we're focusing on the motion of a star orbiting a black hole and all the force of gravity and the interactions of a multi-body system. So in part 1, we're given the trajectory of a star with mass 2 times 10 to the 30 kilograms, which is about the mass of our sun, and the star is orbiting a black hole, which is at the origin. So basically, our goal is to use the observed motion to work backward and estimate the mass of the black hole. So to do this, we defined our time step here as delta t, which is 86/400 seconds, which is 1 Earth day between the recorded positions. So as you can see here, and then next. So our foundational principles here are the momentum principle. In its very simple form, it's that the net force acting on an object is equivalent to its rate of change of momentum over time. In our code, we calculate the velocity between the data points and define the initial and final momentum between the two data points, and then find the initial velocities and the mass. So by calculating change in p over t, we can find the total rate of momentum, dp dt, and we assume that gravity is the only force acting on the star right now, which is a pretty crucial estimation. So to get a bit of the deeper look at the orbit, we make the force into two perpendicular components, the parallel and perpendicular. The parallel is acting in the star's motion, so p hat, and then we multiply that by the change of magnitude, which is basically how much it's slowing up or speeding down. And then the perpendicular component, you subtract the parallel component from the total. So this is the turning force, or basically what's turning the star towards a black hole. And once we have the net force, we can solve for the unknown mass. So we say F net equals g times the product of the masses over the distance squared. By rearranging this, we can isolate m ph because the star's orbit is elliptical and the force and distance change at every point. This results in slightly different mass values at each step, but to ensure accuracy in the code, we end up finding an average that will be printed at the end. So here's pretty much all of our code. Firstly, you set all the constants here. Then we run our simulations. This is for part 1 and part 2. And then we're updating the velocity to get the updated momentum. And then we keep updating until we can find the parallel and perpendicular. So then this is our final calculation for the mass. And there it is at the end. And this is just setting our arrows for the simulation, as you saw before. Okay. So what if the imaginary system is a planet, a moon, and a star, and a black hole? So basically, to include all the interactions, it would be a lot more complex. We need to calculate the force of gravity between every pair, so the planet on the moon, star on the planet on the moon, etc. So we use a superposition principle to sum the forces and find the unique F net for each to update their positions and velocities. Thank you.